Hi, this is the VESC-Project 300. Been working on it since about January, a bit now and then, and in the recent months I've been spending a bit more time on it and it's starting to work quite well. So let's take it apart and see what it looks like inside. As you can see, the design is quite similar to the VESC-6. So we have the power stage up here, and we have three inputs, actually three outputs for every phase in parallel, and three inputs. And the reason is that it's quite a bit easier than having really thick cables, and it also makes it easier to make the power stage nice and symmetric. So let's take the PCB out and look on the other side. So we have the same direct fed package as the VESC-6, but in this case we have 75 volt FETs. We also have a different shunt amplifier. Instead of the AD8418, I moved to the INA240, and well, that's actually the component that sets the lowest voltage besides the MOSFET in this design, and this one can go to 80 volts, so I went for the 75 volt MOSFETs. Otherwise, the DC-DC converter can go up to 100 volts, and the shunt or the MOSFET drivers can go up to 120 volts. Going back to the other side, you can see that we have, instead of having an integrated driver, we have three separate drivers. And the DC-DC converter, the first one, that goes from the input voltage, actually steps the voltage down to 12 volts. And the 12 volts are used to drive the gates, and then they are stepped down to 5 volts and 3.3 volts. And one advantage of this is that unlike the DRV chips that have a linear regulator to provide the gate voltage, this one doesn't have nearly as many losses, so we can switch a lot faster. Actually, I've been driving this one up to 70 kilohertz using FOC, and well, I couldn't go higher because then it consumes too many computations. But I do have a test rig with a motor that really likes high switching frequency. Let's go out and have a look at it after, well, assembling this one. Oh, I can also mention that if we go back to the other side, we can see that we have, well, actually cannot see it on this one yet, but actually can, maybe you can see it there. I have been experimenting a bit with a low pass filter on the current measurement, and that is really convenient to have when you have a really low inductance motor, especially on low modulation, because you have so high current ripple, and then when you sample the current, then it might not be the true value, and it will especially not be the true value when you have high input voltage and low modulation on such a motor. And this helps a lot. So the final design that is on pre-order right now actually will have three analog switches, so you can switch on and off those low pass filters on the current measurements. And the reason that we need to be able to switch them off is that to use the power stage to measure the inductance, we need to have a really low latency on the current path. And if we want to drive the motor, we can have as much latency as, well, the latency doesn't really matter as long as it doesn't get too high when we drive the motor at high speed. So for example, if we have, I did some simple simulations, and if we have, say, 50 nanofarads and 1K as an RC filter in this case, then at 106,000 ERPM, I think we get something like 10 degrees phase lag, and that should still give us more than 95% or 90% or so of the torque. And we could also compensate for this phase lag. But, well, to measure the inductance, there's not so much we can do. Well, I tried some tricks in software to compensate for the phase lag of the filter, but it didn't really work out reliably, so that's why I opted for the switch. So I'm out of my garage now, and this is the motor that I will test. Now the reason it's quite difficult to run is the low inductance. This is my LCR meter, and we set it to inductance and set the frequency to 100 kilohertz. We can connect two of the phases of the motor, two of the phase wires, and this is the other one. And as you can see, we have 1.3 microhenry between two phases, meaning that the phase inductance is something like 0.65 microhenry, and that is just crazy for a motor. Just to give you some perspective, I have here a cable about this long, a bit more than half a meter, I think, or maybe it was even a bit less. And if we connect this one, we get, see, let me also untangle it. So we have a loop. We get about 1 microhenry, and that is almost the same as between the two phases on the motor. So this motor really behaves like we have a short circuit of a 12 AVG cable of this length, and that is quite unbelievable. Also the meter, if we just put the probes together, you can see that we get 0.01 microhenry. So it is quite well calibrated, and I'm just surprised that it works at all. Actually, when I connected this motor the first time, I didn't expect it. Actually expected it to kind of blow the fats up in an instant, but that did not happen. And I think at this point I will probably burn something like 10 kilowatt hours testing this one. So this is the setup I have. You can see I have my 2 kilowatt Escom power supply, and I turned this one to 55 volts. It should go to 60, but for some reason it doesn't output more than 55 volts because it just shuts down if I turn it up more. And this one is connected in parallel with a 14S LiPo pack, which consists of two 4S LiPos and one 6S LiPo, and those are 16 amp hours. So they kind of act as a buffer when we need to draw more current. And this one, when we start drawing the current, is when we charge them up to, well, reach the level they had before, the same voltage as this one. When you do this, you have to have a multimeter handy and measure the cell voltages of them now and then so they don't run out of balance and cause a fire. Another thing I have here is this 500 amp shunt, and this goes to Victron energy something current and voltage meter, and that one I can use as an independent power and current measurement unit, and then I can compare, for example, BLDC with FOC and different switching frequencies to each other. And since the current is quite low frequency here, this one should keep up with whatever is happening on this end. And then I can, since I have a fan that moves air and I run RPM control, then I can in theory compare the efficiencies, because a certain RPM should always draw the same power. So if we, for example, go between BLDs and FOC and see different power levels, then we can see that the one that has lower power output for this RPM probably has the higher efficiency. You can also measure that the VESC can measure the RPM quite accurately, because it's based on, it has to track the motor anyway, and it's based on the crystal in it, and I think this one is 15 ppm. So we have a really accurate RPM measurement, and we have a repeatable input power measurement. So let's move over to my laptop and have a look and give it a run. So now I'm sitting at my laptop. Down here I also have this energy meter that I mentioned before, and it also has a backlight. And I have connected VESC tool to the VESC now, and I also added an experiment page, and this page you can connect to an external monitor. So I can go ahead and connect to this one, and we see that it reads 55 volts in and 0 amps. And we can, well, let's go over to the real-time data, and I will give it 300 amps. Now I can mention that at this voltage, this motor cannot push 300 amps because it doesn't get enough voltage to get the speed, so I think it goes down to something like 250 amps. But at 250 amps, I think we have something like 10 kilowatts input, so let's give it a try. Yeah, so I have it a bit over 10 kilowatts input, and Actually, we probably had more than that for a while, but this one is quite slow to update. And when we had the 10 kilowatts, we were at 247 amps on the VESC. If you look at the graph, you will see that if I give it the command again, we actually go up to 300 while we accelerate, and then we go down to 250. So now you see when we are at this level, then we are at 250 amps, and we reach 300 up there. Now, the reason that the voltage or the current is slowly dropping is that the power supply voltage, the input voltage decreases, and that is because the batteries get discharged, and then once I let go, the power supply will charge them up to the level they had before. So they kind of act as a buffer to provide more peak power and also to take some power when we do braking with the motor. Now let's go back to this experiment page. So we have a few functions here. We can do a few sweeps. Well, someone is calling me. Be right back. Alright, so this page in VESC Tool has, this is a new page for experiments, and this is also where we connect to this external monitor. And it has a few sweep functions in duty cycle, current and RPM. And for this setup, the RPM sweep is the most useful. So we'll do a sweep from 5,000 eRPM up to 60,000. And this is a 10-pole motor, so meaning that this means that we have a fifth of that mechanical RPM, which would be about 12,000. And this sweep I'm going to do 1,000 RPM per step, and we're going to run each step for 1 second. And we also get we can plot this while we run the sweep and see what is going on. On this plot we have a few options to switch on what we want to draw, and now everything is switched on, so I'm going to switch off. No, actually let's keep everything on, and then I can point on the graphs after that. Struggle a bit starting there. So you can see the red one, on the red side is the RPM that we step through, and switch off the motor current, and then you can see the temperatures here. Actually, I will talk after, it's so loud now, I don't think you can hear me. I'm losing where those. Alright, so now you can see that we have a nice graph here. This is the power, and as you might expect, it is kind of not linear, because the faster the motor spins, the more you have to increase the power per RPM to maintain the speed. And we can, as you can see here, we can switch on and off the different graphs. Another thing we can do is that we can export this graph to either a CSV file or a PDF or a PNG. The CSV file, even if you don't have everything active, it will store all the data. So let's export this one. I will put it on my desktop and just call it test. And what you can do with this kind of setup is that you can actually open a CSV file to compare and load the test one here. And then you get the same colors, but in dashed lines. And suppose we are interested in, not interested in duty cycle, we're only interested in the power and the MOSFET temperature and the motor temperature. And yeah, nothing else. Then we get a bit cleaner graphs. And now we want to compare BLDC to FOC. So then we go to the General tab, switch the mode to BLDC. And we also have to invert the direction, because FOC and BLDC spin in different directions, and otherwise the turbine is not spinning, or the fan is not spinning in the direction it's supposed to. So write the configuration. And let us do the same experiment again. I can mention I already did the detection, and BLDC is more or less as tuned as it will get for this kind of motor. And you can immediately see that actually the power is dynamic scaling, so once we get over 120 watts, we'll probably get a little close to this graph. And here is the result. As you can see, that FOC really benefits in the low speed. You can see here the dashed line, which is the FOC. We have consistently lower power all the way. And as we get to the highest speed, then BLDC gets quite close to the FOC result. But it's a lot more noisy across the whole spectrum. And I think I prefer FOC quite a lot over BLDC mode. Actually, let's try exporting this graph. We can give it a title. Let's call it BLDC vs FOC. And the first graph is BLDC. You see that the legend updates as a type in those boxes. And here we have FOC. And store it as a PDF file. Also, we can choose the resolution for the files. Let's just store it as ASD then. And going to the desktop, we can open this in the document viewer. And this is a nice way to share the results. And everything is vector graphics, so not bad. Also, I have a touchscreen on this computer, which is really nice for working on the app, which I also have done a lot on, probably like 4,000 new lines of code. I will show that in another video. Let us actually run another test. So I'll go back to FOC mode, not inverted direction. I can mention a few things here. First, I can mention the test I want to run. So what I want to test is I want to see for how long I can run before something overheats and we back off in current to not overheat the things. And what I can mention is firstly that in this case, I have a 1 millimeter thick heat pad under the MOSFETs, because that's all I had laying around. And the final version will have a 0.5 millimeter, so it will probably be better at conducting heat. And second, since I have this extremely low inductance motor, we run at 60 kilohertz switching frequency, meaning that we probably have a bit more switching losses than if we run like 30 or so, or 20, which you might do for most, well, more normal motors. So let's go to the experiment page, and this time we're just going to run a current sweep. And we're going to start from, say, 180 amps. Well, let's start from 250 actually and make really small steps. Go up to 300 and take 2 seconds per step. And every step can be, say, 0.5 amps. And this should give us plenty of time to run until something overheats. I think this is 50 amp steps in 2 seconds, so we have 100 steps times 2 seconds, so we will run for 200 seconds in this test. So switch on backlight and let's go. right, so you can see that we ran for 180 seconds, or was it 200? Yeah, and the MOSFET temperature got up to 90 degrees right away, and we started throttling the current, and we could sit at around 180 amps. Now, what this hardware also has is it has individual MOSFET temperature sensors, and we can switch them on, and you can see that two of the MOSFETs were at 80, and one of them, this is actually the middle FET, went up to almost 100, or like 90, 95 something. So I'm over on this side now, and you can see that we are charging with almost 2 kilowatts. And the batteries are a bit warm, but not that warm. And let's move over to motor. Yeah, this one is really warm to touch. And the VESC is not that warm. This aluminum bar probably helps a bit too, that it's attached to. So now I'm standing on the other side. And I don't know if you can see the clock on the wall, but when I switch it on, I'm going to switch it to 300 amps, and it will go down to 220 so at this voltage. The clock usually starts to move quite a bit. I will also put my hand over the motor, and I think you can see kind of the airflow by just looking at how I have to struggle to get my hand close to it. So let's run. Yeah, so this one is quite powerful. I think it can lift something like 20 kilograms. We can also move the camera back a bit. And I don't know if you can tell from here. Let's refocus. But you can kind of see that those two bars that are welded up on this table, so they will also bend a little bit when I give it full power. So let's give it a try. So let's investigate what happened to the temperatures before. This is the plot I had from the run in the garage, and you can see that in the beginning, actually let's have a look at where the temperatures are measured. So we have the temperature of MOSFET 1, which is the first group of 3, then we have the temperature of MOSFET 2, and then of MOSFET 3, and they're measured like this. This is the PCB, and on the bottom side, down here, R21 is the NTC that measures the first group. And then if you turn the PCB around, we have R49 up here that measures the second group, and R51 that measures the third group. And going back to this plot, we can see that in the beginning the first one was a bit higher, and the reason is probably because since we sit down here, we get a bit of coupling to the rest of the electronics. Whereas these two, that is on the other side here, only measure the true temperature of the MOSFETs. And they also start out exactly the same value. And then as we push current, we see at some point the outer two diverge. And I think the reason is that this one here is actually the one in the center. And the reason that this one gets warmer than the others is quite simple. Simply because those MOSFETs are getting heated up by both these ones and these ones. I can also mention that these, since they sit next to the edge of the case, they also get a bit more aluminium out here where the case comes to conduct the heat away. And the reason I plotted all three, or the reason I investigated this from the beginning at all, is that first I only plotted the highest temperature, a filtered version of it actually, and I saw that always around this point it looked like we got some noise, and then we suddenly started increasing temperature faster, and I was thinking that we had some ringing on the gates. I didn't know what to do about that. I tried to use different gate resistors. I tried changing the dead time. I tried putting a Schottky diode parallel with the gate resistor, and no matter what I did, it would always look the same. And then I plotted all temperatures, and I saw that, yeah, this was the thing that was going on. And the thing that happened is, of course, that first we tracked this one. It's higher because it's close to electronics, and at some point we start tracking the highest one, and that's why we get this shape of the temperature that is sampled together. We can also have a look at another test I did a few days ago. And in that test, let's plot the motor current too. In that test, actually the MOSFET temperature was not the limiting factor. We can see it was the motor temperature, because first the MOSFETs got warm and the motor started to catch up in temperature, and we had to decrease the power to keep the motor temperature below a certain limit. I think I set it to 85 degrees here, and then I made another test the same day and increased the motor temperature to between 90 and 100 degrees. And we see that we have the same profile at first, and then first we get the limitation because the MOSFETs get too warm, and here we are at over 200 amps, so I think I probably had more clamping force at that time. And then the motor temperature caught up and we had to do limited modulation or the power output because the motor got too warm. So I think this VESC is quite well matched to this motor. And remember, the motor had a lot of airflow since it is an EDF and it sits in the middle of this high pressure airflow. And again, the final hardware is going to have the 0.5 millimeter thermal pad, so I think it can probably, hopefully, do 300 amps continuous. But even so, it should be able to do 250 at least, and 300 for 20 seconds or so, and that's not too bad at all. So that's the updates I have for now. Thanks for watching.